Example 1, graph the set of all x elements of the set of integers such that the absolute value of x plus 2 is less than or equal to 3. All right, we've already done these problems before. It looked like this before. Graph the absolute value of x plus 2 less than or equal to 3. Domain equals x. Domain equals the set of integers. All right, so we've already done these problems. It's just a different way of writing the same problem. One slight difference in the structure of the problem is that before we just had absolute value of x, now we got the absolute value of x plus 2. Okay. So let's focus first of all on our absolute value expression here, our whole inequality that we're looking at. Anytime you have absolute value bars in an inequality, ideal step 1 is to get the absolute value expression, whatever it is, less than or equal to or greater than or equal to or whatever to a positive number, ideally. All right, if it's to a negative number, then it's either going to be all real numbers or the empty set. All right? But if it's less than a positive or greater than a positive, it's doable. But it doesn't matter what's inside the absolute value bars. Our goal is to get the absolute value expression all by itself, nothing else attached to it, no minuses, no numbers being added or subtracted from it, but just the absolute value expression of whatever, doesn't matter. It could be absolute value of rhinoceros, doesn't matter what is inside there, just as long as it's the absolute value expression all by itself. Inequality symbol, positive. Okay? The two scenarios are this. Either we get less than a positive or we get greater than a positive. Those are the two scenarios that actually matter to us. In the situation of absolute value of expression, all right, less than a positive, we do it this way. We're going to get negative less than the expression less than the positive. If it's expression greater than positive, it's going to be expression greater than positive. Just get rid of the absolute value bars, that which everybody wants to do anyway. Just get your eraser out and erase them. Okay? Or expression less than negative. So looking at the picture we have here, we have the less than a positive structure, right? So we're going to use this structure to create a non-absolute value expression, okay? I don't want absolute value bars in my inequality. They're there. I can't make them go away just by erasing them. But because again, here's some of you guys' technique on how to get rid of absolute value bars. You get your eraser and you do that and you pretend they aren't there. Okay, that's illegal. You cannot do that. You can't just say, I don't like absolute value bars, so go away absolute value bars. That's not legal. This is the legal way to make them go away. Whatever this number is, make it negative, less than or equal to, same symbol. If it has the equals, put the equals. If it doesn't, don't. All right? Then the expression without the bars, less than or equal to, then the positive number. That's how you make the absolute value bars go away legally. All right? And again, up till now, this type of problem, this would have been x in the middle, we're ready to go. We're going to graph what we were looking at, okay? But now, this says x plus 2. My overall goal every single time in these problems is to get x in the middle. I don't want x plus 2 in the middle. It's there, I can't make it just... Again, I can't use this technique to make the plus 2 go away. I don't like your plus 2 go away. That's not legal. You can't do that. So, but you have to, algebraically, using legal algebraic technique, make it go away. If I want 2 to go away, I subtract 2. There's 1, 2, 3 pieces, so I got to do minus 2 here and minus 2 here to allow that. The inequality is structured correctly. If I change 1 by some number, I got to change everything by the same number. 2 minus 2 cancels, making the 0. X plus 0 making x, making what we wanted in the middle. Negative 3 minus 2 is negative 5, and 3 minus 2 is positive 1. So here is the correct solution to the inequality. Our last job now is to graph that. So once I've gotten all this taken care of, so again, I took the inequality structure, I simplified it down, I got rid of the inequalities legally, I made x in the middle legally, and I got my answer. Now I got to graph my answer. Now is when the domain matters. Set of integers. The way we graph integers is closed circles on every single true answer. That's how we graph integers. Okay? Starting with the endpoints, negative 5 equals, and negative 5 is an integer, so I'm going to put a closed circle on negative 5. positive 1 equals, positive 1 is an integer, so I'm going to put a closed circle on positive 1. X is less than 1 and x is greater than negative 5, so x is right here in between those two numbers. Every integer in between those numbers is getting graphed. And there's my entire answer. Let me just show you one extra thing here real quick, in case this should happen. If this did not say equals to, so this was not there, and this was not there, the only difference in the answer would be this would not be graphed, and this would not be graphed. I'm not going to put open circles because I'm not trying to get close to negative 5 or 1. They're just not included because just bigger than negative 5 is not an integer. Still not an integer, still not, still not, still not. There's the first integer that's true. Just less than 1 is not an integer. Still isn't, still isn't, still isn't. Now it is. First integer, first integer. That's what happens with the equals to. So again, the equals to isn't there. That's how you handle it. In this case, we did have the equals to, so we do graph the negative 5 and the positive 1. So that's the whole problem. Again, we've done these before. They just didn't have that structure in the original question. So they're done the same way we did them in the past.